The fifth order Taylor polynomial approximation of f of x at x equals 0 is given to us. It says P5, and so that's how we know it's a fifth order because of that 5, is 15 minus 12x plus 9x squared minus 6x cubed plus 3x to the fourth. And then the question is, what's the third derivative of the function at 0? We have some options, minus 36, minus 1, 16, or 36. Do we have an answer? A? Does that sound good to other people?
Yeah.
Okay, you're right, it's A. And there's two ways to do this. So one way, I'll jump to method 2. Because method 1 I think is the better way. So let me talk about method 2. So what is the Taylor polynomial? Like, what's the intent of the Taylor polynomial? So the intent of the Taylor polynomial says, I want to behave like the function. And I want to behave like it in the sense that I'm going to match the derivatives. So if I'm asking a question about a derivative, then the Taylor polynomial says, I'm going to do the same thing, as long as it's up through whichever order we pick. So our order is fifth order, so it says, I'm going to match up to the fifth derivative. So if I want to know the third derivative of f, I just say, take the Taylor polynomial, take 3 derivatives and plug in 0, and that's got to match. So that's the idea. So we're taking P5, taking 3 derivatives, turns out to be minus 36 plus 72x. You plug in 0, and you get negative 36. It has to match f. So that's one approach. Now, another approach, though, is to say, well, you know, what's happening with Taylor polynomials is that I'm storing information about the derivatives. And the way I store it is I store it as coefficients. So what I can do is if I just understand what the coefficients represent in my Taylor polynomial, then I can figure out what my derivative is. And in particular, this is the fifth order Taylor polynomial all worked out. So the coefficients are storing the derivatives. Divide by the order of the derivative. So if I'm after the third derivative, so the x squared stores the second derivative, the x to the fourth stores the fourth derivative, and so forth and so on. So the x cubed is storing the third derivative, so I say, okay, the coefficient of x cubed has to be the third derivative divided by 3 factorial. So now I can just set these two equal, and 3 factorial is 6, and solve. Negative 36. Out of curiosity, for those of you who got it, which way did you go? Method 1? Method 2? Okay, all right. They're half and half, roughly speaking. So that's fine. We're not saying one is superior. Use what works for you. Use what works for you. Now, there is a bonus question up here. Notice that this says P5 of x, but it's not a 5th degree polynomial. It's only a 4th degree polynomial. Is that okay? Okay, I see one person nodding their head yes. It is okay. Why is it okay? What's going on? Now the reason why I'm asking this is some people would think, oh, if I'm looking at the nth order Taylor polynomial, it should be a polynomial of degree n. But it's not nth degree polynomial, it's nth order. Order here is referring to not the degree, it refers to what? So it's a challenge question. Okay, nth order is referring to what? If you're stuck, we can just guess a letter. D is an excellent choice. What? E. It's another excellent choice. R. I'm suspecting some people know this, but they just want the game to go on. You'd like to solve the puzzle? Yes? Derivative. Yes. Excellent. Good. So when we're talking about fifth order, we're talking about fifth order derivative. So why is it okay that it doesn't have degree 5? Well, the fact that it stops at degree 4 is kind of misleading. What is the next term here? 0x to the fifth. And so the reason it has degree less than 5 is really what's happening is that this part right here was 0. So it's okay that our Taylor polynomial has degree less than 5. It just happens that the fifth derivative was 0. Okay. Any questions? All right. Well, we're still working on Taylor, so more Taylor quotes. So, no matter what happens in life, be good to people. Being good to people is a wonderful legacy to leave behind. I once read the transcript of a talk from a very respected scientist. And one of the things that they said, and I'm paraphrasing, but it's very close, is they said, you can either be a great scientist or you can be a nice person. You can't be both. That's stupid. You can be a nice person and a great scientist. I will say that there are plenty of great scientists which are, excuse my language, jerks. But there are also lots of great scientists who are nice people. And here's the wonderful thing for you to know now. People don't achieve great things by themselves. You need people to work with. You need people to collaborate. And this image of this lone scientist somehow changing the world is a wonderful story, but it's not true. You rely on others. And the best way to work with others is to be kind and make friendships and get to know people. Not everybody will be friendly with you, and I don't claim you have to be a friend with everybody, but it's good to be kind. It's good to be kind. All right, so what's our goal for today? Well, we're finishing up our Taylor polynomials. And so we're going to do a quick review of what Taylor polynomials are. So we have our basic formula for Taylor polynomials. And we have our error bound. Now that's stuff we talked about last time. But of course, it's important just to say, what's going on with these Taylor polynomials? We're trying to match the function up through the nth derivative. But then someone would come and say, why stop? We should never stop, never stopping. We should just keep going, match them all. Go all the way. And that's the idea of Taylor series. So we're going to say what's a Taylor series is you don't stop at n. You go all the way up to infinity. So another way to think of what a Taylor series is you could say, hey, this is like p infinity of x. It's that Taylor polynomial, but just taken all the way. All right, so the idea is, lo and behold, we're going to match all the derivatives. And we will see that if we do that we're going to match the function. Now, we have to talk about what this means and how we know that equality. And that's a big thing we'll talk about today. And now that we have this, we can start to say, well, what's going on? We can build up our Taylor series. So we can rewrite now some basic functions in terms of series. So e to the x, and I represent as e to the box, just to remind myself, I can put anything in here. I can write that as this series. I can write cosine as a series. I can write sine as a series. And here's the beautiful thing. All three of these, it's true for anything you plug in. So no matter what you plug into the box, that's true. So we can turn any computation involving the exponential function, the cosine function, and the sine function into a computation that's polynomial for all intents and purposes. In terms of our formula sheet, we're basically going to be in this section here where we have the Taylor series for cosine, sine, e to z. And I'm even going to toss this one in. We've talked about geometric series before, but we're going to see that actually it's really a Taylor series. It was a Taylor series the whole time. So that's today. And as a reminder, when we started this part of the course, we had a goal, which was to say, hey, we want to write our function as a polynomial. We started with sequences, infinitely long list of things. We said, how can we add that up? When does that make sense? We then said, well, let's look at power series, which are these infinite polynomials. And finally, we reached the end. Taylor series, where we can turn particular functions into power series, so that we turn problems into polynomial problems. All right. The end is near. Good. All right. So let's get back into Taylor polynomials. So we have a formula. And the nice thing is you don't have to memorize the formula, but it's important to understand what it's doing. So the nth order Taylor polynomial, that's denoted Pn of x. You need to specify the order, so you need to specify which derivative you're matching up through. You need to specify a location. So you're trying to approximate the function at a point, we usually say A. And the way we approximate the function is we say, well, let's mimic what the function is doing. And the thing that we choose to mimic is the derivatives. We're going to match the derivatives as best we can. And when we say, what do you mean as best as you can? Well, I only have, if you think about what an nth order polynomial looks like, I don't have very many things I can do. I can't control infinitely many things because I only have a couple of coefficients. So the best I can do is I can more or less control n plus 1 things, because I have n plus 1 coefficients. We say, well, here's what we'll choose to do. We're going to match the derivatives from the 0th order, which means we'll match the function, all the way through the nth order. And so the Taylor polynomial, if I take the kth derivative and plug in a, and I compare it to the function when I take the kth derivative and plug in a, that will match up through the nth derivative. We make no promises past that point, because it won't. But it matches small derivatives, which means it's doing a good job of approximating nearby. Now, of course, how do we know it's a good job? And that's when we get into error bounds. And it's perhaps not the most exciting thing, but it's an important thing. An approximation is only good if we can somehow argue the error is small, and better if we can argue it's getting smaller the farther we go. So there was a little bit of integration by parts, moving stuff around. We said, well, it turns out that you can bound the difference between the function and the nth order Taylor polynomial by an expression. Well, it depends on your choice of x and how far away you are from a. So there's this x minus a to the n plus 1. There's an n plus 1 factorial downstairs. Win for us. We like factorials downstairs because that is something which goes to 0 quickly. But upstairs, there's this m. And what m is it says, how big could your next derivative be, in some sense? Now, when I say next derivative, remember we're matching up through the nth derivative. We say, look at the n plus first derivative, and not just at a, but near a, between x and a. How big can it get? That's your bound. So, I make a note here. It's roughly look at the next term, right? Because if you think about it, if you think about what does the last term look like, it's the nth derivative at a, x minus a to the n over n factorial. Well, this is looking at the n plus first derivative at some point near a, x minus a to the n plus 1 over n plus 1 factorial. Now, the good news is you don't have to remember the error bound. That's also on the equation sheet, but it's good to know it exists, and you need to know how to use it. So let's work through a problem. Find the second order Taylor polynomial p2 of x for the function f of x equals 1 over x centered at x equals 2. So there's a couple key things here. How far do we go? That's second order. That's also reflected in that 2. And of course, you also need to know your center. So that's here. So make sure you understand how far are we matching the derivatives, where are we centered at. So if we're after a Taylor polynomial, what we need to do is start gathering information about derivatives of our function. It's a second order Taylor polynomial. How many derivatives are we going to have to look at? Or how far do we have to go into the derivatives, if you will? 2, right? Second order, the order says how many derivatives you're matching. Okay, so we have our function, f of x, 1 over x, which, by the way, is the same as x minus 1. So we're going to look at some derivatives here. What is f prime of x? Negative 1 over x squared. You can think of it as bring this negative 1 down. That's where that negative comes from. X minus 2, or negative 1 over x squared. That's perfectly fine. F double prime of x, because we have to match up to the second derivative. What will that be? So now the negative 2 is your exponent. Bring that down. Minus minus 2 makes a plus 2. Subtract 1 from your exponent, negative 3. So that's 2 over x cubed. Now, it's not that we're going to have the functions. We're going to have the functions evaluated at the center. So after we compute the derivatives that we need, now we plug in our center point. So f of 2, f prime of 2, f double prime of 2. This problem is very 2y. That's okay. What is f of 2? We plug in 2 into our function. What comes out? 1/2. Excellent answer. 1 over 2. F prime of 2? Negative 1/4. Beautiful. F double prime of 2? 2/8. Also known as 1/4. All right, so we're trying to create a polynomial such that if you plugged in 2, you get 1/2. If you took the derivative and plugged in 2, you get negative 1/4. If you took 2 derivatives and plugged in 2, you'd get 1/4. Now, the good news is we don't have to think about how to do that because we have this approach. And it says, because you're centered at 2, you should write everything in terms of powers of x minus 2. So in general, our P2 of x would look like, and I'll just write this down, the 0th derivative is just 0, just the function. So f of 2, and then x minus 2 to the 0 is 1. Now go to k equals 1, you get f prime of 2 over 1 factorial times x minus 2 to the 1. Plug in k equals 2, f double prime of 2 over 2 factorial, which is 2, x minus 2 squared. But now we just say, hey, we know these numbers. So we say, all right, so that would be f of 2 is 1/2. F prime of 2 is minus 1/4. X minus 2. Then we say f double prime of 2 divided by 2. That's 1/4 divided by 2. 1/4 divided by 2, also known as 1/8. Now, once we get to this point, what do we do with this? What's the next thing to do with this polynomial? Next thing to do is to put a box around it. Because we have the answer. Because I said, find the second order Taylor polynomial. The one thing you shouldn't do is expand. Expansion actually kind of obfuscates what's going on. And in terms of applications, suppose he says, oh, I want to use the Taylor polynomial to do an approximation. I want to plug in something. Well, if you've expanded, you've made it harder on yourself, not easier. So we found the second order Taylor polynomial. Okay, so that's the first part of this problem. Any questions on the first part? Second part now. Now it says, estimate the error between P2 of x and 1 over x. So in other words, we have P2 of x, which is trying to approximate f of x. And we're told we're going to go between 1 and 3. So if I want to understand the error, what should I be looking at? That's the error. What do I need to be looking at? What would I be interested in? What would be useful information for us? The next derivative! Yes! We want that next derivative, right? Because that's going to help us understand the error. Okay, so here we stopped at second derivative. For the error, we're going to go one more step. So the third derivative, we can get away with 3 primes. What's the third derivative of f? So we can come up here, bring the negative 3 down. And that would be negative 6, x to negative 4. If you like, that's negative 6 over x to the 4th. Now, the challenge, or maybe I shouldn't say the challenge, but the important step in the error is the m. This other part is more or less automatic, so we're putting our energy into the m. So that's why we're doing this. So to figure out m, we need to say, okay, we want to have the absolute value of the third derivative, and I'll use y, which is, by the way, 6 over y to the 4th, right? That's just, I'm taking the absolute value here. When you take something to an even power, it's positive. We're asking ourselves the question is, how big can this get? Now, you might say, Steve, I have bad news. Because you have this divided by y to the 4th. That could get huge. But I don't need to look at all the values for y. Which values do I care about? 1 to 3. That's my question. So how big can this get between 1 and 3? So 6 divided by y to the 4th. If y is allowed to go between 1 and 3, what's the biggest it can get? Which value of y does it? The biggest it can get is 6, okay. Where does that happen? At 1. Notice the y is downstairs. So if the y is downstairs, if I want the whole thing to be big, I want to make the downstairs small. And y to the 4th gets bigger as y gets larger. So you choose the smallest value for y. So this is less than or equal to 6. This happens at y equals 1. Okay, so this is our m. So we did the hard part. We found our m. So now we'll write down what we have. We now can say that the difference between our function, 1 over x, and our approximation P2 of x, between 1 and 3 is less than or equal to 6 times absolute value of x minus 2 to the 3, because n equals 2, over 3 plus 1 factorial, 2 plus 1 factorial, 3 factorial. But we can do a little bit better. How big can x minus 2 be if x is between 1 and 3? You're at most 1 away. So this is less than or equal to 6 times 1 cubed. 3 factorial. Anyone know that one? 6, which gives us 1. So our error is at most 1. Now, sure, it's a very simplistic answer. It's a very, in some sense, simplistic type problem, but we're learning the process, and that's the important thing. All right, any questions? Okay, well, that was our review of Taylor polynomials. Now into Taylor series. Okay, so as mentioned, the idea of Taylor series, it's like Taylor polynomials, except we don't stop. We're going to match all the derivatives at the function, at a. So it's essentially, what have we done? Well, you should think of this. This is our p infinity of x. It's our Taylor polynomial taken all the way up to infinity. So we have the function is the sum from 0 to infinity, k squared at a over k factorial x minus a to the k. Now, the equals here, we have to be careful. How can we tell if that's actually an equals? Because I can write it down, but do I actually know? Well, what's our idea? We can think of this as, let's start and say the function is roughly like the Taylor polynomial. That's the idea. We're doing an approximation. So what we want to say is, well, let's look at the error. And the error, that's something we've talked about, the difference between the function and this Taylor polynomial. We say, okay, let's look at that. And we'll let n get big. So if the error gets small, we get equality. We win. So we say, but look, we can bound the error. So if we can show that this gets small, then we get equality. Now this m sub n, the reason I put a subscript n, is it may depend on which derivative we look at. However, if our error can be bounded regardless of our choice of which derivative we look at, then we win. And that's because besides this m sub n, you have two pieces. One of them is exponential. One of them is factorial. Factorial beats exponential. And so it drives to 0. So if we can argue that our error, this expression for our error, this bound in our n plus first derivative, it doesn't depend on which derivative we look at, we've won. We have equality. Okay, so here we go. Find the Taylor series for the function e to the x. Classic problem, and this is probably one of the most important series you will work with. So, if we're trying to understand Taylor series, we channel our inner Taylor polynomial mindset. When we were trying to find a Taylor polynomial, what did we start doing? We started derivatives, because our goal is to match derivatives. So we need to start taking derivatives. So we have the function. Let's start taking derivative. What is f prime of x? E to the x. How about f double prime of x? Okay, how about f triple prime of x? Have we found a pattern yet? What if I asked you for the nth derivative of x? Could you tell me what that is? E to the x. All right, and I probably should have added at x equals 0. Because you should specify the location. But we start at 0, because 0 is our friend. Okay, so the good news is it's easy to find a pattern in the derivatives. But after you find the derivatives, what do you need to do? when we're doing Taylor polynomials. We found the derivatives, and then we plugged in. So what are we going to do? Plug in. What's f of 0? 1. What's f prime of 0? 1. What's f double prime of 0? 1. What's f triple prime of 0? 1. What's the nth derivative at 0? 1. Ah, good. We see a pattern. So that tells us that when we write this down, that e to the x should be equal to our summation 0 to infinity. Our derivative is always 1. And so we have 1 divided by k factorial. And then x minus 0 to the k is x to the k. So there's e to the x. And I like to think of this as e to something is the summation 0 to infinity something to the k over k factorial. Just to sort of say, there's nothing special about x. I can change it. Now, when this is true, for which values of x does this match? Well, okay. Let's suppose we fix x. So we have 0, and it turns out that the nth plus first derivative looks like e to the x. We didn't write it down, but it's still true. So now let's just put x over here. My question, how big can this get from 0 to x? How big can the n plus first derivative get from 0 to x? What's the largest it can be? As large as it can get is over here. So this is max of the n plus first derivative of x is 4, well, I'll say n plus first derivative of y for 0 less than or equal to y less than or equal to x. Now the reason I chose 0 is that's the center. That's where we're centering around. And we say, okay, that's the largest it can get. This is e to the x. Now, what does this tell us? Well, if we come here and look at our error, so our error is this error here, this m is e to the x. This x looks like x to the n plus 1. And downstairs we have n plus 1 factorial. Now, you might say this is looking bad, but the question is, what are we trying to change? Is it x or n that's changing? Well, it's kind of both, right? But when I'm trying to figure out the error at x is fixed. N is what's going to be big. Now, as n gets big, what happens to the error? This goes to 0 as n gets big for x fixed. Now, the punchline, that says for any x, the error between the Taylor series and the function is 0. That's for any x. So this relationship, this is true for all x. So regardless of what x you plug in to this right-hand side, you get e to the x out. So we started by saying we just wanted a good approximation at 0. And by matching the derivatives all the way to infinity, not only did we get a good approximation at 0, we got a good approximation everywhere. So there we go. All right. Well, let's... any questions? And I will say, this is, again, really useful formula. useful things tend to show up on formula sheets. Well, sine and cosine. Let's start with sine. It's a little bit more tricky than e to the x, so we'll need more space. All right, so the function is sine. What's the first derivative look like? Cosine. What's the second derivative look like? Negative sine. What's the third derivative look like? Negative cosine. What's the fourth look like? Sine. Wait a second. I saw the sine. It's up here. It's opened up my eyes. So this is the fourth derivative. What's the fifth derivative? It's cosine. What's the sixth derivative? Negative sine. And what's going to happen? Well, we're just going to be cycling. So it turns out that when we keep looking at these derivatives, it just cycles through four possibilities. And we could keep writing a lot of stuff down, but in general, we'll say, look, if you look like 4kth derivative, then you look like sine. If you look like a 4k plus 1 derivative, you look like cosine. If you're a number that looks like 4k plus 2 and take that order derivative, you look like negative sine. Or if you're a number that looks like 4k plus 3, take that derivative, then you look like negative cosine. So the derivatives follow a nice pattern. E to the x, really simple pattern, just repeats every time. Sine, it takes 4 steps, but then we start repeating. So let's evaluate. So we have the following. If I look at, say, a 4th kth derivative at 0, and I should have said, and I forgot to specify it, so I added it in here, at 0. Plug that in. That says you plug 0 into sine. Sine of 0 is 0. If I look like a 4k plus 1th derivative and I plug in 0, what comes out? Cosine of 0? 1. If I look like a 4k plus 2 derivative and I plug in 0, what comes out? 0. If I look at 4k plus 3, negative 1. So our coefficients are 0, 1, 0, minus 1, 0, 1, 0, minus 1, 0, 1, 0, minus 1. Well, so let's start writing this down. So sine of x, well, it's going to be 0 plus, all right, so let's just remind ourselves, f of x is the summation, k equals 0 to infinity. We're going to just assume we're at 0. So the kth derivative at 0 over k factorial x to the k. So it's 0. Then the next term will be x, 0 for the x squared. Then we'll have a minus. It'll be x cubed over 3 factorial, because I'm plugging in x equals 3. Then 4 will be 0. 5 is a 1. So plus x to 5 over 5 factorial. 6 is back to 0. 7, there's a minus. Plug in 7. X to 7 over 7 factorial. What's the next term going to be that I write down? 9. Plus or minus? Plus. X to 9 over 9 factorial. What's the next term? 11. X 11 over 11 factorial. And it's a minus. And it keeps going. Now, we'll pause for a second and say, do you notice anything about the numbers that are left? They're odd. Why do you think that happened? Do you think it's a coincidence? No? Okay, so if it's not a coincidence, why did it happen? What's true about sine? Sine is a strange function. It's an unusual function, a weird function. Some people might even say sine is odd. Sine is an odd function. Okay, so it's perhaps not surprising that everything here was odd. In fact, it should have happened. Now, we want to write it in a nice compact way. But notice, we're not going to have everything. We're only going to have the odd terms. So here's our idea. We'll say, let's write it as odd numbers. Now, what do odd numbers look like? Well, 2 times something plus 1. So here's the idea. We'll have x to the 2k plus 1. Because 2 times 0 plus 1 is 1. 2 times 1 plus 1 is 3. 2 times 2 plus 1 is 5. 2 times 3 plus 1 is 7, so forth and so on. Downstairs, we have our factorial going on. 2k plus 1 factorial. Do we need anything else? We need to have something plus minus. And so that's just minus 1 to the k. We don't want minus 1 to the 2k plus 1. Minus 1 to the 2k plus 1 will always be minus. So minus 1 to the k. Now, you can convince yourselves that this works. Write out the first few terms, and they'll match. All right, so this is the Taylor polynomial. Now, how good is it? Let's come back and talk about the error. So, how big can a derivative of sine get? One. Because the derivatives of sines and cosines look like sines and cosines, and they're bounded by 1. So m is at most 1. That's a win. So not only do we have this, this is true for all x. Now that's for sine. So just to be clear, this is our sine x. Now, what about cosine? What can we do? Well, we can repeat the argument, or we can say, you know what? I don't feel like writing a lot of stuff down. I already have sine. What can I do to sine to make cosine? Derivative. And we've already talked about calculus. So, take a derivative. Derivative of sine will give us cosine. And now, how do you take a derivative of a series? Term by term. X is what we're taking derivative with respect to, so we still have this minus 1 to the k. What's the derivative of x to 2k plus 1? Well, it'll be x to 2k, but there's something else. There's like a suspicious gap here. Right, the power comes down. Divide by 2k plus 1 factorial. But is there another way to write 2k plus 1 factorial? Let's think about what we've been doing with things like that ratio test. Yes. Yes, we can pull out a term and write as 2k plus 1 times 2k factorial. And as if it was meant to be, those cancel out. And we get the following. So cosine is the sum, 0 to infinity, minus 1 to the k, x to 2k, divide by 2k factorial. When will this hold? This will be true for all x. Now we mentioned all the powers of sine were odd. What are all the powers for cosine? Even. Why do you think that is? Well, we said sine was an odd function. What's true about cosine? It's an even function. Even refers to symmetry, but it also turns out when you talk about Taylor polynomials, an odd function will have only odd powers, an even function will have only even powers. Okay, so what do we have? In summary, We have 4 basic Taylor series. And you're thinking 4? Steve, you miscounted. We only talked about 3. Actually, we did 4. Geometric series are Taylor series. There's a nice rule of thumb, and it says the following. If you find a series, then it is the series. So it's the Taylor series. So if you say, oh, I have an expression that matches, then you say, great, you found the Taylor series. Good job. Victory for you. So we have our 1 over 1 minus something. It's the sum of something to the n, and that holds for small things. The e, cosine, and sine. Now, if you're asked to find a Taylor series, don't reinvent the wheel. Don't go through and start saying, let me grind out a lot of derivatives. That is the wrong way to go. Adapt what you have. You've invested to get some basic building blocks. Use your building blocks. Now that might mean change what's on the inside of these. Might mean integrate or differentiate. You might say, let me put series together and let me multiply. But the good thing is, we've done the hard part. We found our building blocks. And now we can start playing and putting things together. So we'll do that next time, and we'll stop here for today.